In the beginning of the electrical age, we knew that electric power varied. The first thing we learn in electronics, and the first thing they wanted to know in the early days, was the amount of electricity and how a given quantity can work for us.
When we engineer things and build and test, we make every conceivable kind of measurement you can think of. Behind almost every kind of instrument that we use, there's fundamentally, somewhere in that instrument, there are measurements of voltage and current. And those are the things that allow us to say that the things we've built are going to work.
Early electrical pioneer Alessandro Volta could increase the power of his battery by physically adding more zinc and brine discs for different experiments that required more power. But how could we precisely measure electricity for better experimentation? Electricity is the flow of charged particles or electrons. We can measure the quantity of moving electrical charges or current by the amount of charge passing a given point each second by the effect it creates in the form of Joule heating or magnetic fields. Another pioneer, Michael Faraday, discovered that a single electrified wire generated a magnetic field. Joseph Henry figured out that if we add multiple insulated coils to the same power source, we could dramatically increase the strength of that magnetic field. The first idea developed by early pioneers was to use the strength of the magnetic field generated in a coil to deflect a compass. In this exercise, you can see how an electric current creates a circular magnetic field around the wire. The farther out you go from the wire, the weaker the field, and the higher the amperage pumped through the coil, the stronger the effect. This is the basis for how the ammeter works. Early pioneers discovered that the shape of the magnetic field around a coil is circular and moves in one direction. Now, if we reverse the polarity, we will see that the magnetic field also reverses. This is why you need to hook up an ammeter according to its polarity. Galvanometers were adopted to detect current, and some use a magnetic needle hanging by a string inside of an electromagnet. The more amps in a circuit, the more the needle would move. The device was sensitive to movement, and it was thrown off by other disturbances in the magnetic field. Laying the groundwork for future meters, James Maxwell was able to explain magnetic fields using his equation in the 1860s. With an increased understanding of the mysterious world of magnetism, we were set to build a better meter. In the age of the telegraph, Western Electric and other companies developed some galvanometers for measuring lines, but we needed something better. In the 1880s, Thomas Edison was the first to have many customers attached to one power station, so he needed a way to charge customers for power consumption. Without a good meter, he crudely approximated the energy used by charging customers by how many light sockets they had installed. That was short-lived, and he moved to a primitive electrochemical method. Elihu Thomson and Edward Weston saved the electrical industry by developing a meter that worked in a new way. Instead of using compasses which align themselves to the Earth's magnetic field, they created movement in the needle using the left-hand rule. This is the same concept that makes motors run. This became the basis for the moving coil galvanometer. This type of amp and voltmeter dominated for over 100 years. Let's look at the basic principles for a moment. If we run electricity through a wire set in a magnetic field, it induces movement. We can demonstrate this and build a simple meter using just magnet wire, 2 magnets, a power supply, and some structures. We will use gravity to hold the wires down, but normally a meter will use springs. The wire is suspended in the space between 2 magnets. When we energize the wire, it creates its own magnetic field, which is opposed to the magnetic field created by the 2 magnets. This induces motion. The left-hand rule causes the wire to move up. The more power we put into the wire, the more it moves up. Moving coil galvanometers place an energized coil of wire inside two permanent magnets. A balanced spring keeps the needle oriented at zero with no current in the coil. This construction became the standard for the 20th century and is still used today in many applications. While magnet-based meters worked well on direct current, we need the meters to work for alternating current, so rectifiers are used to convert the signal to a constant positive current. Having an accurate and fair billing system was necessary to get the electrical industry off the ground and lead to the expansion of AC electrical services. While ammeters are useful for looking at current flow in real time, there needed to be a way to measure current and power used over time. Oliver B. Schallenberger was one of Westinghouse's best experts on AC power. He used magnetism to create rotation, and the rotations could be counted, and he produced the world's first watt-hour meter. To make a voltmeter, we can use the same mechanism as an ammeter, but we put a resistor in series with it because we don't want most of the power flowing through the device. The current flowing in the resistor and a sensitive ammeter is an accurate measure of the voltage to be measured. Voltage is the measure of potential energy between 2 points per unit of electrical charge. We can measure voltage with a voltmeter, a ratio potentiometer, or more recently, an oscilloscope. Another way we can measure voltage is by using electrostatic force instead of magnetic force. This method was used often with high voltage. Charges attract and cause movement of the meter vanes indicating the measured voltage. Early ammeters and voltmeters caused a disruption of the circuit that was being measured. However, vacuum tubes and semiconductors revolutionized our universe of instruments. With vacuum tubes and resistors, we could build much more sensitive instruments that did not disturb the circuits and enabled the development of multimeters. Today, using an integrated circuit, we can convert analog signals into digital signals, making an even more compact device. Over the years, many improvements have been made, including the addition of amplifiers before the meter to boost tiny signals, allowing us to see in more detail and use more rugged compact meters. Today, we are even able to count electrons in an extremely weak circuit. Volt and ammeters are a basic building block of many sophisticated marvels of technology, including CTs, MRIs, and photosensors. Learn more about these meters on our website. See more in-depth videos, reference material, and activities at the Universe of Instrumentation website.